everyone. In this video, we're going to wrap up our discussion on acid-chloride reactions. So the first one is reduction. So if we're starting with our acid chloride and we want to reduce it, we're going to use lithium aluminum hydride, which we've seen before, followed by either water or acid to protonate the oxygen. And that's going to give us a primary alcohol. So let's look briefly at the mechanism. We've kind of seen this type of mechanism before, so it's pretty similar to those. We have our lithium aluminum hydride, so we've got aluminum bonded to 4 hydrogens with a lithium atom there to even out the charge. One of the hydride atoms is going to use its electrons and attack the carbonyl carbon, which will move electrons up to oxygen. So now we've got our negatively charged oxygen, our alkyl group, a hydrogen, and a chlorine bonded to that central carbon. So chlorine is a good leaving group, which means that oxygen can reform its double bond, and then we'll just kick out the chlorine there. So here it looks like we have an aldehyde, and unfortunately, lithium aluminum hydride is such a strong reducing agent that we can't really stop at the aldehyde here. We would keep going all the way to the alcohol. So let's just make a note that we can't isolate the aldehyde. So another aluminum hydride molecule is going to come in. And again, one of the hydride atoms with its electrons is going to attack that carbonyl carbon. We're going to move electrons up to oxygen. Now this time we have 2 hydrogens bonded to that central carbon. And in the last step, we're just going to protonate that negatively charged oxygen using our acid or water. Either one is fine. All right, and we get our primary alcohol. So pretty similar to mechanisms we've seen before using lithium aluminum hydride. Now, what if we did want to isolate that aldehyde? Or I guess not isolate it, but what if we wanted to produce that aldehyde and not the alcohol? Well, one way that we can do that is to use a less nucleophilic reducing agent. So there's different ways that you can make a molecule less nucleophilic. In this case, we're going to make our nucleophile bulky. So we're going to still have one hydrogen bonded to aluminum, but the other 3 hydrogens will be replaced with tert butoxide groups. Oops. Also called butoxy groups. All right, and then we still have lithium hanging around to balance that charge. So again, let's see, this is called lithium tri tert butoxy in parentheses, aluminum hydride. So quite the name there. But we can write this as LiAl, and then in parentheses we'll write OR, close parentheses, subscript 3 for those tert butoxy groups, and then we have a hydrogen. Now, again, because this is so much bulkier than lithium aluminum hydride, this is only going to reduce our acid chloride once. So we're going to stop the reaction at the aldehyde. Okay, so let's do a practice problem where we can use this reagent. Let's say that initially we have a benzene ring with a ketone meta to a carboxylic acid. Let me make this a little nicer there. So we're going to turn that into a benzene ring with that same ketone, but our carboxylic acid will be converted into an aldehyde. So again, most of the molecule stays the same, but we're turning that carboxylic acid into an aldehyde. So see if you can figure out the appropriate reagents to use for this reaction, and when you're done, we'll go over it together. All right, so we're starting with, again, that carboxylic acid. We just saw how to turn an acid chloride into an aldehyde. So how would we turn a carboxylic acid into an acid chloride? Remember, we saw that we can use thionyl chloride to turn the alcohol on the carboxylic acid into a chlorine. And luckily, thionyl chloride will not touch the ketone. Okay, so we turned our carboxylic acid into an acid halide. And then how do we turn the acid halide into an aldehyde? We'll use that bulky nucleophile. So lithium, aluminum, OR3H. So that will stop at the aldehyde. Now there is another way that we could perform this reaction. Instead of turning the carboxylic acid into an acid halide and then going to the aldehyde, we could convert the carboxylic acid into an alcohol and then turn the alcohol into an aldehyde. And the way we can do that so again, if we turn the carboxylic acid into an alcohol, we want to make sure we're not reducing the ketone at the same time because this is a reduction reaction, right, from the carboxylic acid to the alcohol. So remember at the very beginning of this carboxylic acid chapter, we said that we could use borane tetrahydrofuran to only react with the carboxylic acid. So that will leave the ketone untouched, which is what we want. Now, in the last step here, to get from the alcohol to the aldehyde, we need an oxidizer. But remember, we probably want a gentle oxidizer to get to the aldehyde. So which gentle oxidizers could we use? So PCC comes to mind, although this is carcinogenic, and other gentle oxidizers have their own issues as well. Some are smelly, some are flammable or, explosive. So that might not be the best pathway on the top, but it still works. Okay, so now the last set of reactions we're going to look at involve carbon-based nucleophiles. So remember, one of our favorite carbon-based nucleophiles is the Grignard reagent. And we can definitely use that to turn our acid halide into an alcohol. So let's say we're using a Grignard reagent with a methyl group attached. Now this is a strong nucleophile, so even though initially we would just add one methyl group, we are going to go all the way to our alcohol at the end. And again, that's because the Grignard reagent is so strong. So this intermediate here is hard to isolate. So we unfortunately can't produce a ketone from a Grignard reagent and an acid halide. However, there is a type of reagent we can use to stop at the ketone, and that is called a Gilman reagent. So a Gilman reagent is slightly different. This involves copper and lithium, and then we have two alkyl groups bonded to copper. And those alkyl groups are the nucleophiles. And this molecule here is called an organocuprate. So the cuprate refers to copper. But in this particular reaction, again, we're going to stop at the ketone. So if you find yourself needing to turn an acid halide into a ketone, we don't use Grignard reagents, we use Gilman reagents. Okay, now let's go over the reaction map for acid halides. We've covered all of the reactions that we needed to, so let's just test our knowledge on those reagents. All right, so I would like you to go through and figure out the reagents you would use for each of these products. So the first one I drew was an ester. The one I'm drawing now is a primary amide. And then we have a primary alcohol. We've got an aldehyde. Let's see. This is a tertiary alcohol. We've got our ketone, and then finally we've got a carboxylic acid. Oops. Oh. Hit the wrong thing. And then we also will want to show how to convert the carboxylic acid back into the acid halide there. So see if you can fill in all these blanks, and when you're done you can unpause the video and we'll go over it together. Okay, let's see if we get the same thing. So if we want to convert our acid chloride into an ester, we'll want to use an alcohol. And then remember, we also want to use pyridine to remove any hydrochloric acid byproduct. If we want to produce a primary amide, we're going to use ammonia. And we don't need pyridine for that reaction because ammonia is a good enough base that it will remove HCl on its own. If we want to produce a primary alcohol, we're going to use a strong reducing agent like lithium aluminum hydride in excess, followed by an acid or water to protonate the oxygen. If we want to stop at the aldehyde, we're going to use that new reagent we learned about, the lithium tri-tert-butoxy aluminum hydride. And then if we want to produce a tertiary alcohol, we're going to use a Grignard reagent. But if we want to stop at the ketone, we're going to use a Gilman reagent. So that has the two alkyl groups bonded to copper and lithium. If we want to turn our acid halide into a carboxylic acid, we're just going to use acid. And finally, if we want to turn that carboxylic acid back into an acid halide, we use thionyl chloride. So I'll try to post something similar on Canvas under study guides, and you can download that, and I'll erase all of the reagents so you can go through and write in each of those so you can test your memory. Now let's do one more practice problem before we go. This is a challenge problem. In this problem, we're trying to convert benzene into the following. So we're actually trying to produce ibuprofen, which you might have used in the past to reduce pain. So you'll notice that there is a tert butyl or isobutyl group para to an alkyl group bonded to a carboxylic acid. So see if you can figure out how to make that product. It's a little tricky, but it is possible. And when you're done, you can unpause the video and I'll show you my synthesis steps, which might be slightly different from yours, but that's okay. All right, so going through this synthesis is very challenging. That's, I guess, why I labeled it a challenge. But the first thing I'm noticing is the carboxylic acid group is on an alkyl group. So those are kind of two separate things. I'm also noticing that the two groups are para to each other, so I want to make sure to add those groups para. So probably the first thing I would do is just add that random alkyl group bonded to the carboxylic acid. Now again, my synthesis might look slightly different from yours, and that's okay. They don't have to be exactly the same as long as you get the same product. All right, so I'm just going to use electrophilic aromatic substitution to add an ethyl group to the benzene ring. Then in the next step, I'm going to use Friedel-Crafts acylation to add an acyl group para to my alkyl group. So here I made sure that I had an orthopara director attached before I added the acyl group, because the acyl group is a meta-director. Now, it is possible for you to flip this. You could have added the acyl group first, reduced it, and then added the other alkyl group. That's fine too. So the reagents here, I would have an acyl group bonded to a chlorine, and then we've got aluminum trichloride as the catalyst. Now, one thing though that I had to keep in mind as well is in the next step, I actually want to add bromine to my benzylic carbon. Because I want to turn it into a Grignard reagent eventually, so that I can then attach a carboxylic acid. So I do actually want to keep my acyl group an acyl group. I don't want to reduce it just yet because the acyl group has a benzylic position as well. So that carbonyl group is acting as a blocking group for now. So that bromine will only add to the ethyl group. Now, to add that bromine to the benzylic position, I'm going to use NBS and heat. In my next step, I'm going to reduce the acyl group. Let's see. I guess it doesn't matter too much when we do that, but I'll just do it here. So we're going to use that zinc mercury alloy with hydrochloric acid. Now I'm going to add magnesium to create my Grignard reagent. And finally, I'm going to attack, or not attack, but add carbon dioxide and acid to turn my Grignard reagent into a carboxylic acid. Oh, oops, I drew my Grignard reagent wrong. I apologize. There we go. So if we add CO2 and acid, remember that will turn that magnesium and bromine into a carboxylic acid. Now again, this is just one way to synthesize ibuprofen. There might be other ways, so maybe you did this slightly differently. So you can always message me your synthesis pathway and I can take a look and see if there's anything that might not work. But otherwise, I think we'll stop here. Next week, we're going to discuss the other carboxylic acid derivatives and how to prepare them and their reactions. So I will see you then.